All right, in this video, I'm going to go over problem 1, version A, which is a question about limits. So they give you two representations. Once again, the AP exam likes tables, graphs, and analytic functions as three different ways of approaching looking at calculus and functions and relations. They give us this graph of f, so f is done as a graph, and g is done as a table. So they tell us that g is a continuous function, but it doesn't give us, obviously, all the values. It just gives us selected values. So the overview of the problem is they ask part A to evaluate this limit. This is, amongst these questions, this is an easy question because it's just asking you to break up the limit. And if you can break up the limit and use the information they gave you, you should be able to evaluate it. They want you to evaluate what's happening as x approaches these four values. Once again, that shouldn't be too bad if you understand the limit concept, being able to answer what the limit is for these four things. It asks if f is continuous at a particular value. If, once again, not too bad of a question if you understand and know the definition of continuity. And then write a difference quotient that best approximates the instantaneous rate of change at 0. This is probably the hardest question because you have to know those definitions of the derivative. But once again, overall, this entire question doesn't have anything that's too crazy. It's all about limits. So let's look at the answers. For 1A, basically all you have to know is that if you have the limit of a difference, you can just do the limit of each function separately and then take the difference afterwards. So basically you just need the limit as you approach 0 of f of x and the limit as you approach 0 of g of x. If you go get those, you can get both of them. One comes from the picture, and so from the picture, both sides are approaching 2, so it's all good to go. And then on this table, they basically also say that's also always increasing, so it gives you a good estimate. Now, they do say estimate, so it doesn't have to be perfectly exact, but the best estimate in between here, zeros in between these two, looks like 2 is a really good estimate for it. So if you just basically go, I know this one's 2, this one's estimated to be 2, so it's approximately 0 is the limit of that whole thing. Once again, we don't know it for sure because we're not positive that this is the value, but they just said an approximation. So you get actually 1 point for coming up with that approximation from the table and another point for the answer. So an easy 2 points. Evaluating the four limits, I just wrote them plugged in. It does say to evaluate them or tell why they don't exist. These two, so f of x at 2 and 4, both have values. F of x at 2, even though the function value is missing. Remember, the limit doesn't need the value to be there, just needs the approach. So both sides are approaching a y value of 1. At 4, basically the function value does exist at -1, and the function approaches -1 on both sides. So the obvious answer there is -1. The ones that don't exist are when you approach 1 and when you approach 6. When you approach 1, right here, there's that break. The left side wants to go toward 1, but the right side wants to go toward a y value of 0. So due to this break, the general limit doesn't exist. And then at 6, they said in the problem there was a vertical asymptote here. So there is an infinite limit. These go up and they become infinity. But remember, infinity is just a way of saying how the function doesn't exist. So even though it's infinite, it actually still doesn't exist. There's no actual number value for it. So to explain 1, you can pretty much just say because the left side and the right side don't match, since the limit from one side and the limit from the other side don't equal each other, you can't have a general limit. And then in this case, you just talk about the fact, same thing, the left and the right don't actually have limits because they're going to infinity. Since they're both going to infinity, the function's going to infinity, but that's just a fancy way of saying it doesn't exist because it gets larger without bound. Part C's probably the more technical one about proving continuity. So they like to ask this or concepts about this so we understand. To be continuous, your limit from the left, the limit from the right, and the function value at that spot or toward that spot need to all be equal. So putting anything with this definition down gets you 1 point. Now be careful that you don't assert that this is true. I just said to be continuous, it must be true that this happens. So I'm not stating that this is true yet. I'm just saying I'm going to see if this is true. Remember, if you don't put some kind of weasel words out here to get out of it, you might want to put little question marks on this or something. Because if you state this just in a line like this without qualifying that you're checking it, they're going to claim, oh, look, you said it was true and it wasn't, and take off for it. So I'm getting out of that by saying, to be continuous, this must be true. Then I go, however, I point out that I'm testing this out, but it doesn't work. So there's one point for putting the definition down. Basically what I'm pointing out here is the limit from, I just did the limit from the left. The limit from the left is -1. It's also the limit from the right. But the limit from the left and the limit from the right are this number, but the function value is this number. So since the function value doesn't match the limits, therefore the function doesn't exist. Now, normally they would write this, since both of these sides are -1, they would probably just write this without the one-side limit. They would just say the limit as you approach -3 is -1, but the function value doesn't match up. And if we go look as we approach -3 on F, which is right here, you can see it's not continuous because you have the approach on either side, but then there's that little hole in it. There's that gap. Remember, you're not continuous if you'd have to lift up your pen to draw it. In order to hop up here, put the dot and go back down, you'd have to lift your pen up. So it's not continuous, but this proves that it's not continuous. And then overall, let's get the number of points here. So it was 1 for the definition, and then 1 for basically this reasoning, and then stating the conclusion. So I don't know why they made this into 2 separate points, but this whole problem was worth 3. And then the very last part was, these would be the difference quotient. So I put these that these are the exact values. To be careful that they don't actually want the exact value. They do say write a difference quotient that best approximates the instantaneous rate of change. A difference quotient is just when you do the slope. You're subtracting the y's, subtracting the x's, and then dividing them. So the fancy name for that is a difference quotient. Basically, it's division with subtraction in it. That's literally what that means. So I wrote these here just to be careful that these are the exact versions. So if you were writing what's the exact version of the instantaneous rate of change, it would be either this one or this one, plugging into those derivative formulas. But these are not the answers. These are the exact definitions. An approximation, the best approximation you can make at 0 is the average rate of change. The average rate of change is that interval that it's on. So in order to make the average rate of change, you want to use y2 minus y1, x2 minus x1, essentially the slope that's by 0, and the best approximation of that is this value, which is the y value and the other y value, the x value and the other x value. So that average rate of change comes out as 1. This would get you the point because you can't leave the functions there, but once you evaluate it, you're good. But if you simplify it, our best guess for what's the slope at 0 is that it has a slope of 1. Once again, that's an approximation. These would be the exact definitions, but they don't want that. This is good enough. It's really a fancy way of saying find the average rate of change. All right, so that explains question 1 of that section. So let's look at question 2, which is definitely more difficult. Question 2 involves this function f of x, and then they tell us, they don't give us all the values, they have that a and b in there. They tell us the graph has a horizontal asymptote at 3 and a removable discontinuity at 2. The removable discontinuity at 2 means basically we should be able to factor out root of 2 in the top and bottom. Basically it means x minus 2 is a factor of the top and bottom. Looking at this equation, x minus 2 is definitely a factor of the bottom. If you factored this out, it'd be 2 times x squared minus 4, which would be 2 times x plus 2x minus 2. So it's definitely a factor of the bottom. It also needs to be a factor of the top in order to be removable. That way we could cancel it off. The horizontal asymptote, to find horizontal asymptotes, that deals with taking a limit as you go to infinity. So in order to have a horizontal asymptote at 3, the way we're going to interpret this is As the graph goes all the way to the left or all the way to the right, we'll talk about all the way to the right just to make it easier. As the graph goes all the way to the right, it's going to want to go toward 3. So the way we say that is the limit of the function, as we approach infinity of the function, it should equal 3, all right? So those are what we need to know to basically, those two pieces of information should be able to prove that the a is 6 and the b is negative 13. We want to know what value will make the function continuous. Basically, if you want it to be continuous, remember the limit from the left, the limit from the right, and the function value has to match. So if the function is not defined at 2, but if we wanted to make it continuous, we could define a value, or basically it's a fancy way of saying, well, let's find what the limit is as we approach 2. Once we know what that number is, we'll know what to make f of 2 to fill in the little gap that will appear. The function will approach it, and then we'll fill in the little hole that appears when it becomes undefined. And then here, what value does f have a discontinuity? That's a vertical asymptote. Vertical asymptotes are different than the horizontal. The horizontals are limits at infinity. The vertical asymptote means the limit as we approach that value has to go, so whatever value there is, it has to make the bottom 0. That way the thing wants to go to positive or negative infinity. We need a value that makes the bottom 0 that doesn't make the top 0 in order for this to happen. So we already have a removable discontinuity at 2. That makes the top and bottom 0. There's going to be another value that just makes the bottom 0. You can get that by the factorization of this, all right? So to look at the answers, because that's the overview. So the most technical stuff's here at the beginning. Since y equals 3 is a horizontal asymptote, it means that as the limit of x approaches infinity, the function has to equal 3. Now, I can also find the limit as x approaches infinity of the function by literally finding this thing's limit. Now, if you use the shortcut, the pre-calculus rule, remember in pre-calc, if we had a polynomial, its horizontal asymptote was you'd look at the biggest powers and then just divide these numbers. So you could shortcut it that way and get basically, without even doing the limit, you could know that the horizontal asymptote has to be a over 2. But it's important to know the calculus way of doing it, just in case, because when doing this problem, they did state, hey, does the person know about the limit going to infinity? So in calculus language, this is how we would write it. What's the limit as x approaches infinity of this thing? It should come out as a over 2. But if you actually try it out, calculus-wise, you put in infinity, you get infinity over infinity. Remember, that's indeterminate. So I'm going to use L'Hopital's rule. L'Hopital's rule says take the derivative of the top and derivative of the bottom. If I do that, I get 2ax plus b. That's the derivative of the top with respect to x, and the bottom is 4x. Once again, I plug in infinity to this, and I get infinity over infinity. It's still indeterminate, so I can use L'Hopital's rule one more time. If I take the derivative this time, I get 2a over 4. Notice there's no x in it now, so if I try to plug in x, nothing happens because there's no x in the problem. So the limit as x goes to infinity of this thing, since it doesn't have an x in it, is just that thing. It's 2a over 4, and 2a over 4 is a over 2. So this proves the limit of this thing as it goes to infinity is a over 2. It's also got to be this value. So these two things got to be equal to each other. If a over 2 equals 3, then you can just multiply that 2 in and you get a equals 6. So basically, the way they do the points is 1 point for recognizing that essentially that horizontal asymptote is 3, and then finding this value, which helps us get to the end answer. So basically understanding that this limit's also a over 2, all right? And then this is enough to prove that it was 6. Let me see which part's next. Oh, showing the negative 13. So I showed the 6, I have to show the negative 13. I'm going to do that using the fact it has a removable discontinuity. So if it has that removable discontinuity, the top and bottom of f of x must equal 0 at that spot. So now the denominator definitely equals 0 at that spot. The denominator does at x equals 2. Since I can plug it in and check that. The bottom of the function is 2x squared minus 8. If I plug in 2 to that, I get 0. So the bottom is 0. See if it makes the numerator 0. Well, this is the numerator. Remember, there's the original fraction. This numerator Basically, this would also have to be 0, too, for it to be a removable discontinuity. I already know what A is. I proved A was 6 from above. So now this whole thing has to be 0. Now, this has to come out 0 when x equals 2, because that's where the discontinuity is supposed to be. So if I plug in x as 2, I have everything but the b value. So now I can solve for the b value, basically getting all this simplified. I get 24 plus 2b plus 2 equals 0. Move all this stuff over, you get negative, I should say move these two over, you get negative 26, and divide by 2, you get negative 13. So this proves the value here. So they gave a point for you recognizing that not only did the bottom have to equal 0, but the top had to equal 0, and then showing the math that proved that b was negative 13. So that whole part A was worth 4 points, and that's how you can get all 4 points. The next part was show that, or find the value that would make f continuous at 2. So we already know that there's a removable discontinuity at 2. What value would remove it? Well, if f is going to be continuous at x equals 2, it's going to have to be true that f of 2 equals the limit as x approaches 2 of f of x. So basically the left side limit, the right side limit is encapsulated in this thing, and it has to equal the function value. So this is what I need to, basically this is the part that was removed. There's a hole at this spot. What do I want to fill it in with? I want to fill it in with this value. So what is this value? What's the limit as x approaches 2 of f of x? Well, it's the limit as x approaches 2 of this thing. I now filled in the a and the b. I'm going to try it out, because normally to evaluate a limit, you can just plug in 2 and see what happens. Problem is I plug in 2 and I get 0 over 0, which makes sense because it's a removable discontinuity. When that happens, there's a factor that causes the top and bottom to go bad. So since this is indeterminate, I can use L'Hopital's rule to evaluate it. You could also factor it. So I didn't factor it. You can factor it and cancel out something, but I just figured L'Hopital's rule is so nice and so easy, I just did that. So it's indeterminate. I did L'Hopital's rule, 12x minus 13, and then 4x, and the 8 goes away. So now when I try it again, I get my answer, because now I can plug 2 into this version, and it doesn't give me something indeterminate. It gives me 11 over 8. So recognizing that you need to find the limit as you approach 2 as a point, and then getting the actual value. So basically, I just concluded if I make f of 2 that special value, 11/8, that will fill in the gap, and the function will continue. So basically, the function as it is, one side's going toward 11/8, the other side's going toward 11/8. In this case, there was a hole there. So long as I define this in here, like using like a piecewise function or something, that'll fill the gap. All right. And then the last question was, where's the vertical asymptote? So the bottom, let's look at it here. The bottom, if you factor this, I mentioned it earlier, you can pull the 2 out. You'd get 2 times x squared minus 4, and then x squared minus 4 factors in x plus 2x minus 2. Now, x plus 2x minus 2 gives us 2 roots, which give us 2 spots that'll make the bottom 0. So one of those spots is 2. The other spot is negative 2. So 2 we already know is a removable discontinuity because we just removed it, right, where we figured out how we could remove it. So it can't be a vertical asymptote. However, the other one, that's our other candidate. Basically, you'll have a vertical asymptote when you make the bottom 0, but not the top 0. 2 makes top and bottom 0. But negative 2 only makes the bottom 0. So that's the answer. So I put at x equals negative 2, and then y, since the denominator will come out as 0, but the numerator doesn't. If that happens, when you start dividing by 0, division by 0 is undefined, but as you get closer to dividing by 0, you start getting something that's either positive or negative infinity, aka it's going to, on the graph, start approaching an asymptote. So by saying this, that I understand that this is the value in y, that's going to get me that point there. All right? So this was problem 1A in its entirety. I feel like this was like easy limit stuff, and this was definitely much harder limit stuff. The important thing to garner out of this is basically the idea of the horizontal asymptotes as a limit, and things about discontinuities. There were three types of discontinuities. There was removable, infinite, and jump. This talks about removable and infinite discontinuities. Jump discontinuities normally come from piecewise functions, though they do. They didn't define the function, they just gave a picture, but there's a jump discontinuity in this problem as well. All right, so there's the problem, there's all the points. Hopefully you got something out of this. All right, till next time, take care.